What are the types of linear scattering? So types of linear scattering, there are two important types. One is Rayleigh scattering, another one is Mie scattering. First one is Rayleigh scattering and second one is Mie scattering. So types of nonlinear scattering. First one is stimulated Brillouin scattering, and second is stimulated Raman scattering. Brillouin scattering and stimulated Raman scattering. The Rayleigh scattering is one of the type of linear scattering. Rayleigh scattering, which is a dominant intrinsic loss mechanism in the low absorption window. Between the ultraviolet and infrared absorption tails. It results from inhomogeneities in the random nature, of a random nature occurring on a small scale compared with the wavelength of the operating light, or signal. These inhomogeneities, manifest themselves as a refractive index fluctuations and arise from material density and compositional variations. The Rayleigh scattering produces attenuation in light rays, and this attenuation is proportional to 1 by lambda to the power 4. So where lambda is the optical wavelength, To transmit higher wavelengths through the optical fiber cable, the scattering is minimized. How the scattering can be minimized? Scattering can be minimized by transmitting optical light signal with higher wavelengths. The Rayleigh scattering coefficient is denoted by alpha scattering is equal to 8 pi cube by 3 lambda to the power 4, 8 pi cube by 3 lambda to the power 4, n power 8 refractive index of the medium, where n is the refractive index of the medium, p square, p is the photoelastic coefficient, beta c is the isothermal compressibility, and Tf is the fictive temperature, and K is the Boltzmann constant. So what is fictive temperature? Fictive temperature is defined as the temperature at which the glass can reach a state of thermal equilibrium and is closely related to the annealed temperature. Rayleigh scattering coefficient can be calculated with the help of these parameters. The Rayleigh scattering coefficient is related to the transmission loss factor, With the help of this relation, transmission loss factor is equal to e power minus alpha scattering into L. L is the length of the optical fiber cable. So as we know, we already discussed attenuation. Alpha is 10 log base 10 1 by T. So T is a transmittivity or transmission loss factor. So if you see, it is clear from equation Rayleigh scattering coefficient, the fundamental components of Rayleigh scattering is strongly reduced by operating at longest wavelengths possible. As we already discussed, in Rayleigh scattering can be reduced by operating with highest wavelengths. Next one is Mie scattering. This Mie scattering is mainly caused by inhomogeneities which are comparable in size with the guided wavelength, which are comparable in size with the guided wavelength is called Mie scattering. So this is always, this is a one of the linear scattering which is always in forward direction. This is one of the linear scattering. Mie scattering is a one of the linear scattering which is all, the scattering is always in the forward direction. There are different factors causes Mie scattering. Those are, first one, cylindrical structure of cable is not perfect. Cylindrical structure of cable is not perfect. Let us say, take one optical fiber cable, fiber axis. So after certain length, the core of the optical fiber cable, the diameter of the optical fiber cable may vary from the starting point to at some point. The core of the optical fiber, diameter of the optical fiber cable may be different from starting to some other point. So this is the cylindrical structure of the cable is not perfect. And second one is imperfection of core and cladding interface. So this is nothing but there may be some imperfections. In the core and cladding interface. And third one is core and cladding refractive index is not uniform throughout the optical fiber cable. So core and cladding refractive index is not uniform throughout the fiber. And fourth one is there are fluctuations in the core diameter. And fifth one is due to bubbles or strain in the fiber. Mie scattering can be reduced by cylindrical structure of optical fiber cable should be perfect, and there should not be any imperfections in core and cladding interface, and refractive index should be uniform throughout the optical fiber cable. The core and cladding refractive index should be uniform throughout the optical fiber cable. RI should be same throughout the optical fiber cable, and there should not be any fluctuations in the core diameter. So core diameter should be uniform throughout the optical fiber cable, and there should not be any bubble or strain in the optical fiber cable. With the help of maintaining proper precautions, we can reduce the Mie scattering. So this is Mie scattering results significant attenuation depends upon the fiber material, and size, design and manufacturing process. This inhomogeneities may be reduced by removing imperfections during glass manufacturing process and carefully controlled extrusion and coating of the optical fiber. And third one is increasing the fiber guidance by increasing the relative refractive index difference. So one important note, by these means it is possible to reduce Mie scattering to insignificant levels.